Okay, welcome to EGR445. In today's class, we will continue the discussion from last class, and I will also try to answer some questions and try to give you some more information on the design. Please understand that the last lessons, lecture and slides are uploaded. Finally, the Zoom did not crash and it allowed me to save the PDF or the PowerPoint slide. So I could upload the PowerPoint slides. So it has all my notes and annotations for your reference. So first question is, what is a blank diameter? Now, when you are going to cut gears, you basically have something called as gear cutting machine. And when you are loading the raw material, are also called as stock, you clearly, if you want to cut a circular gear, you are not going to use a rectangular stock. So you need to actually have some type of circular stock. Now, this blank diameter is the diameter of the stock material. Dia of stock material. So what happens is when you have a gear cutting machine, first, now one thing that you want to understand that many a times the smaller size gears can be cut on or from a round stock. But if you have to make a large gear or a custom gear, many a times your stock material doesn't have to be like circular. So you could have sort of a rectangular stock material, or you can have a rectangular plate. And first thing what you do is you have a milling machine that would actually mill out this. In certain cases, you can actually use a water jet to water jet the material. If you have not seen a water jet and if you want to see a water jet, we have one in the lab. I can actually show you how the water jet works. If you have not used the milling machine, if you want to, I can't teach you how to use a milling machine, but that's an important skill to have. So you should have some hands-on skills on using milling machine or turning machine, lathe, that boring machine, shaping, all those are important mechanical processes that are used in industry. And nowadays, one thing I want to tell you that there is a lot of emphasis on additive manufacturing because of the flexibility and the advantages. However, subtractive manufacturing is still used in a lot of industry. In a lot of conventional industries, still it depends upon the subtractive manufacturing. So probably understanding additive manufacturing is good, but some exposure to the subtractive manufacturing is also nice, because many a times the parts that you design, there is no point in designing a part if it cannot be manufactured. And unfortunately, that's what happens as a new design engineer. You will have some complicated shape, some complicated form that the production engineer would say, no machine can make this. So you have to have some type of background with what the machines can do. Sometimes you have to recommend different types of operations that would achieve those tolerances. Sometimes you have to make sure that those tolerances are not playing against you. For an example, if you add tolerances, there is something called as tolerance stack, which means the tolerances stack against each other, and finally the result is that part doesn't fit. So you have to look at the tolerance stacking. So all these concepts are super duper important when you go to industry. To understand the basic question, the blank diameter is sort of the maximum diameter that you need And clearly this has to be greater. Clearly this has to be greater than not only the pitch circle diameter, but the addendum diameter of the gear. Remember the addendum diameter that we talked about? You have a tooth, you have the pitch circle diameter, you have tooth thickness, and this gives you the addendum diameter. So blank diameter is addendum diameter dia plus clearance. Now, how much clearance to provide, that completely depends upon the type of operation and the type of machine that you have available. Because sometimes you have some warping, and first you need to flush it and you need to perform a primary machining operation so that the blank itself is well within the tolerances before actual gear cutting starts. So blank diameter is addendum diameter plus clearance, and clearance would depend upon the type of operation you specify, type of machine you specify. And this relates to, remember we talked about the error value when we design the gear, E, and type of amount of E or the error that you have in your gear cutters. So does that answer your question? No, so obvious question is how do we decide clearance? So usually I would say 1% of PCD. So addendum diameter plus 1% of PCD is going to give me. Okay. Now what I want to do is I want to talk about the two-stage gearbox. And this is actually an interesting point that I would make. The design for the two-stage gearbox is actually, if you look at the video that is uploaded on Canvas, it has the design of a two-stage gearbox, and the problem is also worked up. So that if you really want to just do the basic gearbox design, you can use that. But what I want to do in today's class is I want to give you some more information, a step further, on how would you actually design a two-stage gearbox, and how would you use something called as preferred numbers to design the optimal stages, and then how would you use something called as the ray diagram to understand what should be the gear shifts, and how would you go from the first stage on to the second stage. And unfortunately, this information is not available in the textbook. So I'm going to use my notes, and I'm going to give you the design process for the two-stage gearbox. That way, you would certainly benefit from attending the class in person. So bear with me for a second. So does anyone know what preferred numbers are? So let me ask you a very simple, how many of you have seen pyramids of Giza? Or so there is a certain ratio between the height of the pyramid and the width of the base, and there is a scientific reason for that. So that is one of the preferred numbers. If you look at the golden ratio, that also is a preferred number, and preferred numbers are used in a lot of engineering applications, either directly or indirectly. So if you look at the gearbox stages are based on the preferred numbers. So I will give you the procedure for the gearbox design, and then at the end I will kind of show you what would be the a simple and a clean way of doing the gearbox. Mechanism, engine design, pumps, gearbox. So here there are notes. This gearbox design can be used for helical gear or spur gear. So, couple of concepts. So, say the question is, so we are going to design a gearbox, and I'm going to invent a question. Design a gearbox for overall reduction ratio of 6. So we have 3 choices. Actually, as a matter of fact, we have 2 choices. We can have 6:1, or which means we can have a pinion that is 1 centimeter diameter, and we can have a gear that is 6 centimeter diameter. We can have something like 3:2. So these are basically 2 stages that you can actually design. Now, some of you may ask me, yeah, there is another option too. I can do 2 and 3. I can do 2 and I can do 3. Now, should I go with 1:6? Should I go with 3:2? Or should I go with 2:3? That is the question. Because at the end, overall reduction ratio is the product of individual reduction ratios. So you get 6 from 3 approaches. Now, the next question is, what happens if I want the overall reduction ratio of 9? So now the question is, what happens overall reduction ratio of 9? Yeah.
How can you have a reduction ratio of 2 to 3? Because that means the pinion is larger than the gear, right?
Oh no, so actually 6:3. What I mean by the first reduction is what I mean by you would have first stage 3:2, and the second stage, so this is 3. So this is so first stage is 3. So this is like this. So you could have 3 in the first stage, and then you could have 2 in the second stage. So it's a 2-stage gearbox. And when I say 6:1, that means this is the reduction ratio. Yeah, I should have said like this. This is the reduction ratio of the first stage. And this is the reduction ratio for the second stage. Does that make sense?
Yeah.
Now here, you have a choice. If you want to go left to right, so this is your input shaft. This is your output shaft. Still, you are going to have reduction ratio of overall reduction ratio of 6. You can also do something like this. You can start with input over here. Actually, no, you can actually change this to 2 and 3, and still you would get 6. So how would you decide how to go? But most important thing is, and that is, you need to keep in mind that the center distance, if they are uh, along the same shaft, center distance could be one of the design criterions, that you want the center distance between the input shaft and the transmitting shaft to be maybe 5 centimeters, 10 centimeters. So that could be a concern. There could be some geometry concern, like you want all these shafts to be mounted in a particular orientation, or depending upon what the design requirements say. So now the question is, if I want reduction ratio, if I want reduction ratio of 9 reduction ratio. So the first question that comes to my mind, it should I have 2-stage gearbox or should I have 3-stage gearbox? Here is a rule of thumb. Never exceed reduction ratio of 3. So the reduction ratio max should be 3 for spur and helical gears. And in some cases, you may go to 4, but very rarely you would exceed 4. But as far as design guidelines goes, you can actually limit the reduction ratio at each stage is equal to 3. Can someone tell me what is the reason for that?
Micro building, we're using the 4-to-1 ratio. I think if we add any more teeth, it would just be too large.
The gearbox becomes too large. And with large gearbox, again, there are issues with size, housing, weight, all that stuff. So usually we recommend not to go beyond 3. Next thing is, there is a something called as the structural formula. So what is this structural formula? This structural formula, this is output speed This is the structural formula. And this is the number of stages. So I'm just gonna repeat this table. And unfortunately, this table is not given in your textbook. You will have to go to a design data book to get this table. If your output speed is 6, you can have 3 in the first stage, 2 in the second stage. And 1 and 3 indicate the number of rays that goes between the, and I'll explain what I mean by rays. Then if output speed is 8, 1, you have ray 1, 2, 2 rays. Then you have 2, which is 4. Then basically you have 4, 1, 2, 2. So then if you have 9, you have 3, 1, 3, 3. So these are 2 stages. These are 3 stages. These are 2 stages. And this is 2 stage. And this goes all the way up to 18. So if you have seen the automotive transmissions, wherein you can have output speeds that gets reduced up to 18 of reduction ratio, then you will see multiple stages. And that's how you, if you have a manual transmission, you know how you shift. So whether you go left, whether you go right, I believe the Zoom has crashed. Yeah, it's unfortunately not letting me join. I'll have to leave. I really hate when that happens, when Zoom crashes. I'm sharing screen. Okay, finally. Okay, so this is the structural formula. And usually if you want more than 18, you will not use the combinations of spur and helical gears. You would go with maybe some type of worm wheel or some other arrangement to achieve reduction ratios that are greater than 18. So in addition to the structural formula, what you have is you have something called as the kinematic diagram. Now let me show you what I mean by kinematic diagram. So kinematic diagram kind of tells you that if you have two stages, how these stages are attached. So basically, this is stage 1 or stage 1 shaft 1. It is shaft 2. And then basically this goes on and on. There is something like called as ray diagram. So the ray diagram is depends upon the number of stages. So if it's a 2-stage, then you will have stage 1, stage 2. And then what you will have is, as you can see in the parentheses, it shows number of rays. So basically you would have 1, and then you would have 1 and 2. Now, what does ray diagram tell us? Ray diagram tells us that if you have a gearbox and if you have multiple stages, what are the possible reductions that you can achieve with all possible combinations? So if you have a first stage gearbox, you can't have more than one reduction. If you have two stages gearbox, what you can do is you can achieve two combinations. So you can achieve speed 1 and you can achieve speed 2. Now, how does that work? So let me show you how does that work. So you have this first stage, and what you can have is you can have a second stage. So here. And what you can do is you can have another gear attaching or connecting to the gear that is offsetted. So now what you can do is you can engage this first pair and achieve the reduction ratio 1. You can engage the second pair. So basically this gear, this shaft, the whole thing gets shifted. So you will have a clutch here, and then you have a shifter assembly. So what this would do is you will disengage, you will have a shifter that will push the gear shaft towards right, and then the second stage or the second reduction ratio, which is RR2, will get engaged. So you can achieve multiple reduction ratios using the configuration that I have shown here. And if you draw a ray diagram, this ray diagram will tell you how many reduction ratios are possible and what stages you can achieve the reduction ratios. So the formula is Z is equal to P1 X1 P2, which is X2. So P's are the reduction ratios, and these are the rays in intermediate stages. So ray here and ray here. So you will see when you design, say for example, if you start working for Ford or GM and you start working in their transmission department, and then you have to design a new Corvette, then the question is how many shifts, if you're designing a manual one, how many shifts you want to have? Do you want to have 4 stages, 5 shifts, or how do you want to design? And at that time, you would go back to something called as the geometric progression. You will look at the structural diagram, and then you will decide the reduction ratios and number of stages that you need to have. So let me give you another important formula, which is for the geometric progression.
So Professor,
Yeah.
seeing as how there's only a few manual transmission vehicles still being sold new, would all of this still apply to an automatic transmission as well, or does this
Yes.
only work on manuals?
No, this works for the automatic transmission. The only thing is in the manual transmission, the shifting is done manually. In the automatic transmission, the shifting is done using the hydraulic systems. So what you have is you have actuators. Those, believe it or not, those actuators, those are actuated using the differential pressure between the different sides of the actuators, and the gears get shifted. That's why the transmission oil is usually at a high pressure when the transmission is running, and basically that actually does a lot of work when it gets the gears get shifted. So geometric progression, the procedure for the stage design is the same whether you design an automatic transmission or if you use the manual transmission. But only in the case of automatic transmission, I have seen that number of stages in the automatic transmission can be more than the manual transmission. And many a times the actual number of stages in the automatic transmission could be different than the transmission stages that are operated by the solenoid valves. What that means is when you operate a solenoid valve, you will have one stage shifting and simultaneously other stage shifting. So basically that is those tricks are played so that the operator or the driver doesn't have to deal with 20 gearboxes or 20 transmission ratios. And it is actually, you have seen this if you ride bike, you have seen many bikes, they have the Shimaru type of gearboxes. They have all the way up to 27 speed reduction ratios with 3 wheels inside, 3 outside, and different types of ratios. Something like that is also implemented in the car transmission, but the transmissions are simultaneous. Yeah, for CVT, everyone knows what CVT is. Okay, so let me give you the geometric equation and then I will. CVT design is slightly different. So geometric progression is max output speed divided by minimum output speed and this is 1 divided by z minus 1. The geometric progression values phi are 1.12, 1.26, it goes to 1.58. And you can see there is something called as R10, R5, R15, R20. So those preferred numbers. So just before I start answering the question, what about CVT? So CVT is something like this. And nowadays, a lot of car manufacturers are dealing with CVTs. The first CVT in the passenger cars was in Nissan Murano that came in 2009. But unfortunately, that was very unreliable. So most CVTs in Nissan Muranos in 2009 used to break before 30,000 miles. So Nissan had to extend the warranty to 100,000 miles on the CVTs. But since then, CVT technology has improved a lot. So what you have in CVT is you think about like you have 2 cones and you have a belt. And this belt kind of slides left and right. So left and right. So this is left and right. And as you can see, if there is input and there is output, so depending upon where the belt is, your reduction ratio is different. Everyone understood this? So initially, think about it. Initially, if the belt is all the way towards right, the belt, if it's all the way towards right, your input shaft is rotating at a high speed, but the output shaft is rotating at a low speed, which means something like you are in the first gear, you have high torque. Afterwards, then this belt starts moving towards left, which means the output shaft speed increases, but the input shaft would actually, the speed would decrease. But unlike gear transmission, this would be a smooth and gradual shift in the speed. That's why CVT transmissions, they are supposed to be smooth. But the important problem CVT transmission used to have was with the brake. This brake, this belt. This belt used to break, and that was causing unreliability of the CVT transmission. But this reminds me, if you have a CVT transmission, there is its sort of brother, which is called as synchronous clutch. So I just have to tell you that as well. So this clutch is something like this. This is clutch. This is input and this is output. So if you look at this clutch, because of the conical shape, the engagement is not sudden. The engagement is gradual. And if you use this is used in synchro mechanism. So that's why this is called as synchronous clutch. And design of transmission itself is a very complex topic. And I certainly hope some of you will get an opportunity to work on design of transmission, design of gearboxes. And that's actually the dynamics, the design, the concepts, they are really fascinating. Any other questions before I go any further? So step one is use the geometric progression. Second, use optimal structural diagram. And using the equation z is equal to t1 x1 t2 x2, where z is the number of steps. This is the reduction ratio for first gearbox. This is the reduction ratio for the second gearbox. And this is called as the gap, which is the number of intermediate lines that you have. So just to give an example, say if your speed reduction ratio is 1/4, then what you will do is you would use 2, 1, 2, 2. This will achieve 4. Then third part is number of gears on each shaft. And fourth part is draw something called as ray diagram. And drawing a ray diagram is an iterative process. So if you draw a ray diagram, you will have to start with a structural diagram. That comes from the structural equation. Then there are rules, just like shear force and bending moment diagrams. There are rules. So number of horizontal lines is equal to or speed of the step. Speed step. Gaps should be given as first stage, second stage, third stage. And then what you need to do is you need to follow the table for nodes and select. So this is a table, shaft, nodes. So you have 1, 3, 9, 1, 4, 9, and 1, 5, 9, and you will have 13 nodes, 14 nodes, 15 nodes, and then what you do is you decide the next step. number of teeth beside the number of teeth. And then you can draw the ray diagram. And then actually ray diagram. And then you have to verify the reduction ratios and speed of output shaft. So these are the steps that you will have to follow. So let me take an example and the things would be clear. So let me take an example and basically it will all make sense in just a second. So I'm going to take an example. Design a two-stage gearbox. Design a two-stage gearbox. And say overall reduction ratio so they will give you an overall reduction ratio or they will give you the step sizes. So they will say that input speed is equal to one. So input speed is 960 RPM. First stage output speed is 144 RPM. And what you can do is design stages. So either they can give you the reduction ratio, say of 6, or they will just give you the input speed and they will give you the output speed. Step 1, based on the input speed, output speed, you want to find out overall reduction ratio. And if overall reduction ratio is 6, what you want to do is, since it's a two-stage gearbox, you can say it will be 3 times 2. It's always a good idea to have a higher reduction in the first stage and lower reduction in the second stage. So you can, now what you want to do is you want to set this problem up something like this. So initially the pinion is rotating at 960 RPM. So you will have gearbox, something like this. So how would the power flow? So this will rotate this gear, gear 1 would rotate pinion 1. Pinion 1 would be attached to gear 2 or actually pinion 2. So sorry, gear 2, and then this will be attached to pinion 2, and this would be the output shaft. So this is how the pair would look like. So when you design, the first and foremost thing that you want to find out, what are the speeds at each stage. So for an example, they give you an input speed of 960. Then since this is the 3 and 2, the speed here would be 960 divided by 3. And the speed here would be 960 divided by 6.
What's the speed on gear 2?
So okay, that's a good question. Pinion 1 and gear 2 are attached to the same shaft. So you cannot have two different speeds. So basically this would be same as 960 divided by 3. Are you with me so far? Now, how would the gear design procedure be different? Believe it or not, when you are designing a stage gearbox, it's like the gear design problem repeated 2 times. So what you want to do is you want to design the first gear pair. So design this, and then use the second gear pair and design this. So you will have to repeat the process for the gear design first stage and gear design the second stage. Any questions here? Yeah.
So if we're not given, sorry, we're given an input speed and we're given a reduction ratio, we can calculate output speed by just dividing the two numbers.
Right. So basically 960 is the input speed. So first reduction would achieve 960 divided by 3. Second reduction would achieve 960 divided by 6. That would be the overall reduction ratio. Any other questions? Let me see. Single reduction. Pair of spur gears, reciprocating compressor. For some reason, I'm not seeing motor shaft. Yeah. Let me take one example for the gear design, and then if needed, I will work out the two-stage gearbox design in next class. I don't think I worked out a gear design from the scratch, right? I just gave some of us solved a problem. So let me actually, I think it's better. So let me first solve. So a motor shaft is rotating. So speed is equal to 1500 RPM. Power transmitted is 15 kilowatts. And the speed reduction, so reduction ratio is 3:1. The teeth is equal to 14.5 pressure angle with 25 teeth on pinion. Pinion and gear are made up with steel with maximum stress 200 megapascals, and design a spur gear drive. So in this problem, and we can assume 25% overload. And this overload is considered because initially while starting, there would be inertia effects. So the power required could be significant. In this particular problem, number of teeth are already given for pinion, and the pressure angle is given, the speed is given, power is given. So to account for overload, P starting is equal to 1.25 times P continuous, 1.25 multiplied by 15 kilowatts. That gives me 18.75 kilowatts. Now let's assume module is equal to m millimeters. So what we can do is we can find out the diameter of the pinion, which is the number of teeth, 25 multiplied by module. We know the reduction ratio, so we can find out diameter of the gear, which is 3 times 25 multiplied by m. And at this point, step number 1 is to see whether the gear is weaker or the pinion is weaker. But the good news is, since gear and pinion are of same material, pinion is weaker. And we will design the pinion. So now the question is, we want to find out the pitch line velocity. Vp is equal to pi times d times n divided by 60. Now we have a problem. The problem here is, at this point, we do not know the diameter of the pinion. So, or the pitch circle. So what I would do is, I will substitute 25 times m multiplied by n, which is 1500 divided by 60. Pitch line velocity is going to be in terms of module. Now the question comes is, how do I find out the velocity factor when my pitch line velocity is not known? So how would I find out velocity factor when the pitch line velocity is not known? So at this point, what you want to do is, you want to kind of think, how would this gear pair function? So 1440 RPM, pinion is 25 times module. What do you think would module be for 18.75 kilowatt? Just guess. Would it? I'll give you some numbers. You'll get good at it. So I will give you numbers. Would a 1 millimeter module work? 18.75, 2, 3,
Yes, 6.
4. Why? Because that is what is given in the book.
No. Oh, is it?
Yeah.
Oh, wow.
So, but so I tell you the problem there. They guessed, and they guessed it right. But if we were to design, we won't be able to guess it right. So let's think about it. So 18.6 18.75 kilowatt is a decent size power. It's not a very small power. So if you are going up to 5 kilowatt, you would usually expect to see about module from 3 to 4 millimeters. If you go about 5 to 20 kilowatt, you would see modules somewhere between 4 to 6, 7, 8 millimeter. If you go beyond 20, 25, then you are going to see really big module like 8 to 10. So with that in mind, I would suspect, I would guess the module would be somewhere between 5 to 8. I don't know the exact number. Module will be something in between 5 to 8. But that's okay. Now my question to you is, what would be the pitch line velocity for module 5? So what I want you to do is, so assuming m is equal to 5, what would be the pitch line velocity? And if the module is 8, what would be the pitch line velocity?
For M5,
Yeah, for m is equal to 5, what would be the pitch line velocity?
9800.
So 9.8 meters per second. And for 8, 15.7 meters per second. Out of this, which velocity would give you maximum amount of dynamic load? So for an example, you have velocity at 9.8, you have velocity at 15.7. You agree with me, 15.7 velocity is more dynamic than the 9.8, which is about 10 meters per second velocity. So I can safely assume my velocity factor, and for this, I really want you to take a look at the velocity factor equation. I want you to look at the velocity factor equation. And that equation is given on page number 1039. So 1039. Can you see that there is something called as ordinary cut gears 12.5, and there is something called as very accurately cut gears and ground metallic gears operating up to 20 meters per second. Do you agree with me? So you have a choice. And I will do this exercise just for this very first problem. CV is equal to 3 divided by 3 plus 9.8. And you have CV is equal to 6 divided by 6 plus 15.7. Quickly tell me these two values of CV.
First one is 0.234.
The next one is
276.
so which one would you choose? This will make sense in the next step. And I need to discuss this because this is where the students would have issues. I'm just writing the equation for the stress. Stress is equal to B multiplied by pi multiplied by M multiplied by Y. Remember, this is the beam strength equation. Y is equal to 0.124 minus 0.684 divided by T, 0.124 minus 0.684 divided by 25. So please tell me value of Y real quick. Zero point
0.0966.
and I'm going to write down the values that I know. So sigma, so maximum strength for this particular problem is given as 200 megapascals. So this is this guy, 200 multiplied by B multiplied by pi multiplied by M that we don't know multiplied by 0.096. WT is the tangential force. Tangential force, and this is where the things become interesting. Tangential force is equal to the torque divided by diameter of the pinion divided by 2, because that's what we are designing. So torque is power that we found out already, 18.75 multiplied by 60 divided by 2 times pi times 1500. dP by 2 is 25 times m divided by 2. That gives you the equation for WT.
Why did you put that at 60?
Okay, because power and actually I need to multiply by 1000. I actually took a shortcut. P is equal to 2 pi n T divided by 60 because it's given in RPM
Oh,
and power is in kilowatts. So to convert that into watts, I had to multiply by 10 to the power 3. I just took a shortcut. The point here is, understand, you have an M floating around on the left hand side and you have an M that is floating around on the right hand side. Do you agree with me? For the only first problem, what I want you to do is, I want you to assume B. So what do you assume as B? What, 10 times M? Good enough? B by M ratio is 10. 8 to 12 is for spur gear. So 10. So I can write here 10 times M. And I would write here, I would repeat this. I'll first do it for 0.23 and I would repeat it for 0.27. M 0.096. If you are good with calculator, tell me what is the value of WT. So you should tell me a number on the top divided by M. 9.55. No 10 to the power 3 or anything, right? Just 9.55. Anyone else? You got the same answer? So what is this? Yeah, this problem is similar to the problem solved in the textbook, but if you haven't done designs, you just won't be able to follow the steps. Basically, what they do is, let's assume 6, and 6 works out to be great. That will never happen. So let's make some mistakes and then yeah.
I just had a general question. Instead of like how you were just doing, like, let's assume 6 or 5 or 8 or whatever, could you just leave M as an unknown and like you know, leave M unknown in your CV equation and solve for it?
I will certainly do that. No problem. But the question is, what CV equation would you use?
Oh,
There is a trick for that, but let me answer this. So this is our first gear design problem. So I want you to be at the end of this class. I want you to be so comfortable that you can look at the problem and you will have an intuition like, probably this is the size of gear I would be using. This would be the module. This would be the number of stages. So let's do this. So tell me this number, 9.9.55 divided by M. This is very important exercise, at least in my opinion. Is that what you got? Online students, can you tell me this number, please? Real quick. We don't have a lot of time. And this problem is solved in the textbook, but I wouldn't recommend solving the problem the way that is given in the textbook. Multiplied by 10 to the power 3 or anything? No? Okay. All right. So now here is what we are going to do. I am going to find out two values of M from this equation 1 and equation 2. And tell me what you get. And I promise you that your modules are going to be very close. So both of them will converge towards one answer. So this is what I expect. There is one last comment which I would. So now just to answer this question, what if I keep CV in terms of equation? The problem there is, and this problem will be evident if you look at page 1039, CV values are different for different gears. Are you okay with me so far? But here is a trick. And I will tell you what the trick is. I learned this a hard way. 3.3 V and the velocity Vp is less than 12.5. CV is equal to 6 divided by 6 plus V when the velocity P is less than 20 meters per second. If you have carefully cut or very accurately cut, and ground. And see, this is very important. CV is equal to 4.5 divided by 4.5 plus V for carefully cut up to 12 VP is less than equal to 12.5. This is ordinary cut. So the question is, in this equation, WT is equal to sigma naught CV times B times M times Y. Out of these three, which one should I choose? And VP is equal to pi times B multiplied by N by 60. And that is pi times 25 times module times 1500 divided by 60. So in other words, your VP equation would contain module, which means your CV equation would contain module, which means you are going to have module floating around here. You are going to have module floating around here, and you are going to have module floating around here. This equation you will have to solve using trial and error. That is absolutely fine. If you want to go that route, then I would strongly recommend that use this as the number. And make a statement that our gears, the gear that we are designing, will be accurately cut and ground. And then use the value of CV as this. But then you should do this exercise by hand. You will have module appearing on the left hand side, and you will have module appearing on the right hand side, and you are going to get a very complex quantic equation that you cannot solve ordinarily. You will have to use some type of trial and error. And believe it or not, you are doing trial and error here, but this will give you answer quicker. But I would encourage you to try this. So finally, did you get answer for the module? Anyone got module? Online students? So apparently these should give you somewhere between, one will give you 5.2, or other will give you 5.4 or something, and then the module gets modified to 6. That's why module is 6. And that is what is used in the textbook. But this is something I wanted to tell you, because many a times you will have to go through sort of design iterations before you actually figure out what the actual value is. That's it for today. I'm going to stop here, and I will see you on Tuesday.